And basically you integrate them by integrating each piece, and you differentiate them by differentiating each piece. So it's a bit like Calc 1, Calc 2. You just do 3 questions for the price of 1. So what we're going to look at now is one particular application of differentiation, and that's how to find the equation of a tangent line in 3D. So imagine that you've got your classic 3D space, and this red curve is your space curve. And we've got one particular point, say it's this point here, call it P. And at this point P, there is a tangent line. I don't know how well I've drawn it. Now that green tangent line is in 3D, right? So it could quite easily be coming out of the board. So if you're trying to wonder what a tangent line is, here's a little analogy which brings out the Scottish in me. Imagine that the red space curve is the path of a roller coaster. And at point P, the roller coaster is broken, right? It's missing, it fell apart. This green line, right? This line that's going to become the tangent line, that's the direction you shoot off to your death as you zoom off the edge of the roller coaster. So you can imagine you're doing the loop and that, and then boom, off you go, right? Now you see that would be a direction, wouldn't it? Be a 3D direction, depending on how the thing was curving and so on at the time. And we're trying to find the equation of this tangent line. And it involves a derivative, and it involves the usual equation of a line. Now, there are 2 things you need for the equation of a line. Don't you need to know the direction vector, which I typically call V, right? And let's say the direction vector is ABC. And the second thing you need to know is a point on the line. And I typically call it P, and it's going to have coordinates x0, y0, z0. Now, if I know the direction of this green line, right, this direction vector for it, and I know a point in the line P, then won't the parametric equation of that line be, so the equation of the tangent line, it will be x0 plus at, y0 plus bt, and z0 plus ct. Agreed? I mean, that's just revision, really. So now I need to put in the question and show you how it's going to work. So let's suppose we have a space curve. This one is similar to question 11. And the space curve is the square root of t squared plus 4, pretty ugly. The natural log t squared plus, I don't know, 6, and t. And we are interested in the equation of the tangent line at the point P, whose coordinates are, let's see, 2, they're going to be 2, log 6, 0. There we go. Now, of the 2 things that I need, don't I already know one of them? A point on the line. And it's really nice if they tell me the point on the line, but you know, they could have done it another way. Couldn't they have just said at t equals 0? And at t equals 0, if I plug it in here, do you see I get the point on the line? So sometimes they'll tell you the coordinates of the point, and sometimes they'll tell you the value of t. If they tell you the value of the t, plug it in here, and this will give you the coordinates of your point. So getting the coordinates, number 2, is pretty straightforward, right? They either just tell you it, or they tell you a t number which you can use to get it. Now, how do you think I'm going to get, number 1? How do you think I'm going to get the direction vector? It involves something we've already done yesterday.
Derivative?
Yeah. If you think Calc 1, if I wanted the equation of a tangent line, wouldn't I find the derivative of the curve at the point? And that would give me a guy called m, the slope. Well, if you expand that into 3 and 4 dimensions, isn't the derivative vector kind of like the equivalent to the slope? But it's not a vector rather than a single number. Now, I need to get this guy, which means I'm going to have to differentiate these 3 things, which might not actually be that easy, but here goes. If you want to differentiate t squared plus 4, so I'll just put it over here as working. It would be a good idea to call it t squared plus 4 to the power of half. Would you agree? Because if you want to differentiate some, don't you have to have fractional powers, right? You never leave things as square roots. Do you recognize that as a chain rule question? So it's derivative, which I'm calling that. I wish I'd called that f of t, but too late now. Multiply by the power, reduce the power by 1, times the derivative of t squared plus 4, which is 2t, and then you make it look pretty. Well, the 2 and the half cancel, the t's good, that comes down stairs and gets turned back into a square root, and we have t over the square root of t squared plus 4. Check. Okay, the next one I'm going to call f of t. I want to find the derivative of that guy. Okay. This is also a chain rule, isn't it? It's a log of some function of t. And the derivative of a log is 1 over the thing times the derivative of the thing. And so if I want to make that pretty, guess that's the best I can do. So that's going to go in my second slot.
I think it's t squared plus 6, not t squared plus t, right?
Oh. Yeah, fixed. Just a 2t over t squared plus 6. Thank goodness the last one's 1. Would you agree that was an easy derivative? Now, there is a problem. It might not be obvious yet, but this needs to be numbers. Now, if they give you the information at t equals 0, don't I just plug 0 in here? If they give me this guy, don't I have to figure out what t would give me this guy? See, imagine the question only told you all this guy again. And they told you the point. Won't I need to find out who the missing t is? Now, you already know it's 0 because I told you, right? But pretend I didn't tell you. How would you find out that it was 0?
Use the z.
I would. match up any one of the three, whichever one you think's the easiest to solve. In this case, wouldn't t equals 0 be the easiest to solve? But pretend that was something ugly and it wasn't easy to solve. Couldn't I have said this guy equals 2? Actually, no, I've seen that. This guy should be. No, that's it. And this guy equals 2 when t is 0, right? Square both sides, subtract 4. So it was 2. Right, now I know that I'm going to use 0. The direction vector is 0 over that thing, which is just 0, 0 over that thing, which is just 0, and 1. I wish I'd picked a better question, but actually it's pretty much a copy of the question 11 they've got. So I've got everything I need. Let's see what the space curve for the equation of this line looks like. It's going to be A plus 0t. It's going to be B plus 0t. And then it's going to be that guy plus 1t, which gives us a very, did I say log t there? Log 6. There I go with my eyesight again. There we go. And t. Do you know that would just be a vertical line going upwards? Yeah, I could. Can you imagine a space curve? The roller coaster is broken. And do you know the roller coasters that sometimes go like this? Right up the way, right? Look at this thing. Wow. You just get killed there. Whoa. Right. So you would shoot vertically upwards. So to find the equation of a tangent line, you need to know a point and you need to know the direction vector. You can get the point because they will tell you, or they will tell you t equals 0, whichever one they decide they're going to tell you, give you. And to get the direction, it's a derivative of the space curve evaluated at whatever this t value is. And you put those together, boom, you got your answer. Okay. So let's make up a question to do that. Okay, so I need a space curve. So Emma, give me a nice, don't make it horrible because we have to differentiate it, function for the first part of my space curve.
E to the 5t squared.
E to the 5t squared. Okay, it's going to be awkward. Rory, can you give me anything for the middle one? Keep it simple.
E to the, I don't know, 3t.
Okay, I'm picking the next one because you lot are just going to pick e to the something. So I'm not going to have an e to the something. I'm going to have a sine t plus 2t plus 1. Right, so there's my space curve. And we're being asked to find the equation, like the equation of the thing at t equals 0. I'm picking that because it's easy to calculate. So let's find our point. Well, that's going to be e to the 0, e to the 0, sine of 0 plus 2 lots of 0 plus 1. And you get 1, 1, 1. You see how easy it was to find the coordinates of the point if you tell me that guy. Now, I need to find the derivative. Well, that's going to get you 10t e to the 5t squared. This is going to get you 3 times e to the 3t. And this guy's going to get you a cosine t plus 2. And then we just evaluate the derivative at, in this case, 0. And that will give me my direction vector. So 0, 3, the nothings, nothing, that's 1 plus 2, 3. And so the equation of our line, our tangent line, is going to be 1 plus 0 t's, 1 plus 3t, and 1 plus 3t. And if we simplify that down, it's 1, that guy, that guy. Do you feel comfortable about the process of finding the equation of a tangent line when you're given a space curve and a place to do it? Either t equals 0 or the coordinates of P. Are we good? Right, let's just show you what some of the homework questions look like, in case there's one that strikes your eye as being, I'm not sure what that looks like. I'll make this a bit bigger, I think. Right. Now, the way the space curve is written is that they separated the X, the Y, and the Z. Are you okay with that? That's just basically the space curve written down X, Y, and Z components. Can you see the point P? And you're going to write your equation in here. So they're doing it what's called, I think they call this in the textbook, the coordinate form. So it's basically going to be 3 plus 2t, comma 5 plus 5t minus 6 plus 0t or whatever, right? That's what's going to go there. If you look at this equation, they've told me P, which is nice, but I need to know what T equals as well. What value of T would generate this coordinate?
Zero.
I would use Z again and get 0. Doesn't that guy have to equal 1? Right. You can always do it in your head. E to the something equals 1. Oh, the something has to be 0. That makes negative 2t has to be 0. Oh, that just means t is 0. This one is much similar, oh, different numbers, but isn't that very similar to the 11 I did a minute ago? So we'll skip that one. A whole load of t's, right? And e to the t's and all that good stuff. Can I tell you that t equals 0? Would you be able to do that? Simple derivative, product rule, product rule. Not just a product rule. Wouldn't this one especially have a product rule? And when you come to differentiate e to the t6, you're going to have to use a chain rule as well. So just be careful with your derivatives. There's a lot going on here. And that's kind of the end of that particular puzzle, right? Was there anything in those, what was it, 3 questions? Find the equation of the tangent line that you're not comfortable with, or can I move on? Good. Thumbs up will do me. Okay, next question you're going to look at, and I'm glad it's in front of me because it saves me having to write the question down. Find the parametric equation for the tangent line. Oops, wrong one, sorry. Here we go. 2 parametric curves, R1 and R2, intersect at the origin. Find the angle at which they intersect to the nearest degree. Okay, so here's a new puzzle. I know 2 space curves. Excuse me. I'll write down what they are again. The first one is a t, a 3 take away t, and a 35 plus t squared. And the second one is a 7, oops, different variable, 7 take away s, s take away 4, and s squared. And we're being told that these two guys intersect at the origin. So I don't need to find out where they intersect. We're being told that. So can you imagine that might be R1 of t. And R2 of t, you know, comes in and it does its thing. Looks like that. And right there, they intersect. If I did a blow-up version of it, can you imagine that it might look something like this? We're being asked to find the angle that they intersect at. Now, if you're wondering how do you do that, it's all to do with derivatives. Now, I am going to find, or we're going to find, the derivative of the green one and the derivative of the red one, right, the two space curves, at the origin. And what that will do is it will give me two of those guys, right, two vectors. Do we know how to find the angle between two vectors? Right? That's the guy we're looking for. The angle between the two derivative vectors. So there's a little issue that I need to do before I start doing all the clever math is I need to know the value of S and the value of T that makes these guys at the origin. So look at this fella here. Oh, I didn't swear. But it's fixable. I did my scanning problem. I looked at question 13 and I took some of the stuff from 13, and then I looked at question 14 and I took the rest of the stuff from 14. So what I've really got here is these two guys, but they don't intersect at the origin. They intersect at the origin was a different question. So I can keep this bit of the question, which is the functions. And everything I said about finding the two derivatives is correct. But we have a different problem now. I don't know that these two guys intersect at the origin. In fact, I'd be amazed if they did, but they might. I guess they might. We're being asked to find first, where do they intersect? And then I can do my derivative stuff. So here's our problem. This guy and that guy definitely intersect somewhere. But where? Right? Now, can you imagine this is one of the space curves, that's the other space curve. Aren't we essentially trying to find that? Right? And we know they do intersect because of the way the questions worked. Now, if you take the x coordinates, you get t equals 7 take away s. Great. That's the x coordinates. If you match the y coordinates, don't you get 3 take away t equals s subtract 4? And if you match the z coordinates together, you get 35 plus t squared equals s squared. And I check something not right here. According to these two, they don't intersect ever. Yet the question's phrased as if they did. So let me figure out what the heck I've done wrong now. I'm not on a great day for getting things right. Okay, so go back into this question. It's not meant to be anywhere near as difficult as I'm making it out to be. Right. Nothing wrong with the question. Let me try this then. Okay, we got it. That's question is that I wonder if I went and stuck an equation from one and an equation from the other. That would be dumb, but
Why don't they intersect?
oh, if you take the two equations and you add them together, oh, you get 7 equals 7. But I don't get anything useful. Okay. I
But if you
panicked over nothing.
Yeah, if you solve for the y and put it into the z.
It comes out fine. I panicked because I was going to just add these two together and solve for t, and then I added them together and the s and t's disappeared. But it's okay that they disappear because it's 7 equals 7. Okay, so if you take, I know, equation 1, and you match it with equation 3, what I can then do is I can put
You
t.
need to share your screen.
Oh, okay. I probably need a joke after this so I can just focus. So you take equation 1, which says that t is 7 minus s, and you put it into equation 3. And what do we get? We get 35 plus 7 take away s squared equals s squared. And if you FOIL this out, you get 49 take away 14s plus s squared equals s squared. Oh, that's nice. 70, I got 70, I got 84. If I subtract 84 from both sides, and divide, check that comes out as a nice answer. And it does. Now, if I know s is 6, if I go up here, then I know t is 7 take away s, t is 1. So how do I find the point? Well, if I return back to these guys here, won't t equals 1 and s equals 6? And we have got what we needed. Okay. So after a little hiccup and a panic that I shouldn't have bothered about, it came out fine. You take your two equations, you match the x's, you match the y's, and you match the z's, and somewhere out of those combinations, you should be able to solve for t and s. So I need to know the point of intersection. If you plug 1 in here, you get 1, 2, 36. If you plug 6 in here, you'll get 1, 2, 36, right? So it's the same answer. So let's find the direction vector of this fella. Well, his derivative is 1, -1, 2t. Let's find the direction vector of the second line. -1, 1, 2s. At t equals 1, this guy is 1, -1, 2. At 6, this guy is -1, 1, 12. So the angle between these two, which is called theta, is basically going to be the angle between these two vectors. So what we'll do is the dot product divided by the magnitude of this one, which is 6 times the magnitude of this one, 144, 146. Technically correct, it's cosine of theta. What do you get? -1, -2, 24, so that's 22. Okay, I'm about to do the calculator. The missing angle is going to be that guy. Check them in degrees, which I am. Inverse cosine. 22 divided by a bracket, square root of 6 times square root of 146. Sounds all right. Okay. Can anybody see any arithmetic mistake in what I just did? Because I can't. I can. It's a 2. Oh, wait a minute. No, it's not. Still a 1.
What did you get in the calculator?
I get error.
I got 41.98.
I got the same.
I got the same as Sam.
Oh, darn it in space. Let me find out. I do inverse cosine. Nothing much I can do wrong there. 22 divided by, put a little bracket around it, square root of 6. Oh, maybe that's what I did wrong.
I think it's the bracket, Professor. Yeah.
Yeah. Well, moral of that story is be careful, right? I should check my name just to make sure I remember who I'm called. Okay. Do you know what my name means in Gaelic? All good Scottish names, male names at least, tend to be quite good. So Donald means proud warrior in Gaelic. So, right. You don't want to be called Cecil. That's not Gaelic, that's English. But if you were called it, Cecil probably means he who runs away a lot. Okay. After that one, I need to do another one that is got any of those problems, okay? So how many do I have? Oh, darn it, we only have 2. Okay, let me make up one. That's dangerous, but I should be able to do it. Let's have this fella here. T squared, t cubed. Let's have this one. I'm going to cheat a little bit. So I want 1, 1, 1 when I'm finished. So let me guess equals 2. There we go. So the question is, find the angle at which these 2 space curves intersect. And if you set it up, the equation 1, t would be equal to s minus 1. Matching up the y's, t squared would be 2s take away 3 If you match up the z's, you get t cubed equals s squared minus 3. Can we just cut to the chase? And can I tell you that that's the solution, because I made it that solution in the first place. But essentially, if you try and match them up, couldn't you plug that one in and get a quadratic and then solve the quadratic? And one of those works. Evidently that one works and the other one doesn't. So you know there's only one solution. So you find the place where they do it, and that allows me then to take the derivative. And at t equals 1, this is 1, 2, 3. And then I do the second guy. And he would be 1, 2, 2s. And that would be the vector 1, 2, 4. And so we're interested in the angle that these two intersect. So it's going to be the dot product, those two guys, over 9, 10 square root of 14, 16, 21 square root of 21. 1, 4, that's 5. 5 and 12 gets you 17. So the missing angle is the inverse cosine of this ugly fraction.
Can you remind me where we get the square root of 14 and square root of 21 from, please?
Yeah. You take the magnitude of this vector. So 9 plus 1 plus 4 gets me square root of 14. 16 plus 4 plus 1 gets me square root of 21. So this is the magnitude of the first vector, and this is the magnitude of the second one.
Cool, thank you.
Right. If you want to see it as a formula, it would be the dot product of those two divided by the magnitude of the first one times the magnitude of the second. That's what it would look like. In this case, I'm going to hopefully get the correct number of brackets. So inverse cosine of 17 divided by a bracket square root of 14 times square root of 21. Yay! Now I get a sensible answer. To one decimal place, 7.5 degrees. So these two space curves meet at a point. And if you wanted to know what the point is, you could just plug it in. It ends up being the point 1, 1, 1, because I wanted to make my life easy. So they intersect at this point with coordinates 1, 1, 1. That's the derivative vector of the first one. At that point, this is the derivative vector of the second, essentially the angles. And then we find the angle that they meet, and it's 7.5. Okay, that was really quick, but it took out all the confusion, right? It just shows you the process. We feel comfortable about those two questions then. How to find the angle at which two space curves intersect. So now we're moving on to integrals. And we've actually touched on them, so they're not too bad. If I asked you to find the integral from 0 to 2, and the space curve, it was 3t, t squared, e to the t. Yeah, e to the t then, dt. You could write it like that. You could also write it Are you comfortable with both notations, even though I tend to almost do everything using the dot notation, right? In fact, quite a lot of the questions that we've been doing were using this notation. I just converted them into that when I was doing. So space curves, for instance, can be written like this as well. Well, isn't the trick here to integrate each one separately? And when you integrate a space curve, right, a vector like this, isn't the answer a vector? So let's see. I like this notation, so I'm going to do that one. It's integral from 0 to 2 of 3t. The integral from 0 to 2 t squared. And it's the integral from 0 to 2 of e to the t. Okay, 3 upon 2 t squared evaluated at 0 and at 2. That gets you 4, 4 cancels part of that, that gets you 6. Okay, it's the first one done. 1/3 t cubed evaluated at 0 and 2, that'll get you 8/3. And e to the t evaluated at 0 and at 2 gets you e squared minus 1. So the process of integration of space curves, isn't it just do the thing 3 times? Now, this is a definite integral, so it has limits of integration, so you expect numbers. If it had only been this guy, right, an indefinite integral, wouldn't the difference be that your answer would look like this? Have you noticed that the unknown, the arbitrary constant, is called C1, C2, and C3? Can you remember why we need to use different versions for each one?
Excuse me, they could be different for each separate derivative or
Yes.
integral.
Correct. Now, to make WebAssign happy, that is totally acceptable, but would you agree that is mathematically exactly the same piece of information? And now if you write it this way, doesn't it look a little bit more like a single plus c, but it's a plus c vector rather than just a plus c? Hopefully it accepts both, but just in case it doesn't. Right. So for the last few minutes, I'm going to try and tell you what the heck it is. And it's not that obvious. And the reason it's not that obvious is let's return to the 2D world first. If that's A and this is B, isn't the integral from A to B of some function dx, isn't it the area under the curve? Right. Isn't that a definition of what you're finding when you find the integral from A to B, right? It's the net area under the curve. Now, if I stick this thing in front of it, doesn't that end up being the average value of the function? In other words, it's a number probably around about here, right? Maybe a bit higher. Okay. So how does that help me figure out what the vector that you get when you do this guy? Suppose you do it from t equals A to B. Can you imagine that this is where the curve is at t equals A? And then in 3D world, it does it ziggy-zag, right, out and out of the board, and it finishes up here. And the space curve goes like that. Okay, now this thing up here is a vector, right? And let's just call it V, right? And it might be 1, 2, 5, right? It ends up being numbers, right? Because you have a start value of the finish. You might think to yourself, what on earth is that vector 1, 2, 5 telling me about this space curve? Well, can you imagine that to every single point on that space curve, you got its direction vector, right? Its derivative. If you found the average of all of them, it would be pointing in that direction. So give you an analogy. Can you imagine that this is the flight path of a jet? And you'd like to know what's the general direction that that jet is traveling in, right? Because it's zigging and zagging so people don't shoot it down, right? If you're a jet pilot and you're going to bomb someplace, it's probably a bad idea just to take off and go straight to the target. Because if you're flying straight like that, it won't take many people to figure out where the heck you're going, and won't it be easier to shoot you down? So you can imagine, especially for big chunks of the time. Well, if you do the integral of this fella, what you're finding out is that the general direction is that way. 1, 2, 5. So it doesn't tell you anything about the area under a curve. It's nothing to do with area. It's more to do with average value of its direction, average value of where it's trying to go to. Now, if you have a really clever computer and it's got radar capabilities, couldn't you find an aircraft that you're interested in and plot its location for lots and lots of different times? And you've got a little model of this. Couldn't you eventually extrapolate where it's heading? Even although at any given point in time, it might be heading totally different from where it's trying to go to. You know, if you took a snapshot, it's going that way, right? If you took another snapshot, it's going that way. But in general, it's trying to go that way. So you do actually know where it's going.
Did you say that it is the average of all of the direction vectors, or the average of all the derivatives of the direction vectors?
It's the average of the direction vectors. Right, which is the derivatives. And we're using two words that are the same thing. If I say to you r dashed of t, isn't that the derivative vector? But isn't the derivative vector at t the direction at that point? So it's the same guy.
Okay, that makes more sense. Thank you.
Yeah. So I think that's kind of clever, isn't it? If you know enough and you've got a fast enough computer, you should be able to tell where anything's heading if you have enough data points. More likely, can you imagine that they're watching a new asteroid, right? A new asteroid comes into detection range, right? One of the satellites see it. One of the first things they do with those darn things is, don't they record where it is over time? And why are they doing that? They're trying to figure out where the blinking heck it's going. Because if it's going to go somewhere over at Mars, they don't care, right? But if it's heading anywhere near us, don't we kind of want to know? So you can imagine finding some point. Oh God, I hope it doesn't travel like that. That would be really weird. But you could imagine an asteroid might travel like this. You'd still kind of want to know where it's heading, wouldn't you? There would be a usage of it. I think this is a good point for me to say hi if you haven't already. And tomorrow we'll do some more integrations. Maybe I won't make so many mistakes, but nah, that's probably not going to happen. Okay, bye-bye guys. I'll hang about for any homework or any other questions.
Thank you.
You're welcome.
I do not have any questions.
Nothing. Are we good then?
I have a question.
Yay! Been ages since anyone had a question. I was beginning to get worried. Most of the time I was happy because it means you know what the heck's going on. But I was getting worried that it might mean that you don't know what's going on. Right, what you got, James?
Let me see if I can get it. It's way back at the
Is it
First
something I
homework.
did today or homework when you mean way back?
Homework first
Okay.
last week. I think it's format that I'm having trouble with, but I'm opening it up.
Okay. I just seen James and Sam next to each other on my little screen. Douglas, back me up here. Don't they look quite similar, like they could be brothers?
Yeah, they look like twins.
Yeah. Now you can decide if that's a compliment or an insult. That really depends on how ugly you think the other person is.
Okay, so
Okay, what you
it's
got?
find the cosine of the angle between the planes.
Oh, the cosine thingies, yes.
S-
Have you found the unit vector?
So I found the unit vector.
Okay. So what was that unit vector equal to? Because getting the cosine angles, as we call them, is pretty easy. The alpha, beta, and gamma. So have you got some numbers for me? Square roots and whatever it might be.
Let's see what I did. Oh, I'm looking at today's homework.
Anyway, while he's doing that, what you would have, if I set this up while he's looking for the details, in case you're wondering what the question might look like, is that it sounds to me like you were given two planes, right? That's plane one.
Yeah, plane one,
and plane
two.
Right. And what you've got here is a line that forms when these two planes intersect. And this line has a direction, right? And in a unit vector form, it would be whatever I'm about to be told. Now, once you know that, there's things called the direction cosines, cosine alpha, cosine beta, and cosine delta. So cosine alpha, cosine beta, and cosine delta. Alpha, beta, gamma, I should say. If your unit vector, let me just put in some numbers. If your unit vector,
sorry, you need
you
to
got
share
it?
your screen. Oh, never mind, you don't.
Right. Have you, right. Let's suppose that the answer was 2, 1, 2. And it was 2/3, 1/3, -2/3. Let's just say for argument, that's the unit vector of this thing, right? So you might get this vector, but it probably won't be this guy. Can you imagine? It might be 4, 2, -4, right? But when you convert it into a unit vector, it looks like this. Right, now, how do you find this vector? This vector I'm calling V, right, this red one. You get the cross product of the normals to the two planes. And the reason why that works is both of these planes have that red line in them, right? That's the intersection. Won't the normal be perpendicular to it in both cases? So you're looking for a vector that's at right angles to these two guys, and that's how you find it. Right, so that's your answer. Whatever your unit vector is, cosine alpha is 2/3, cosine beta is 1/3, and cosine gamma is -2/3. Now, if you have to find alpha, beta, and gamma, just take the inverse cosine of 2/3. To get beta, the inverse cosine of 1/3. And to get gamma, the inverse cosine of -2/3. And there's no reason in the world why they add up to 180, because they don't typically.
I think it could be the right problem. I may have done it wrong, but if it says find the cosine of the angle between the planes, wouldn't that be?
Oh, that's not these guys then. I didn't hear you correctly. The cosine of the angle between the two planes, you don't need to do anywhere near as much as that. You just need to find the angle between the two normals.
Yeah, so that's what I did. I mean, I could have done it wrong, but
okay. Do you have the numbers for the normals? We can go through the question. If you don't, I'll just make up numbers and show you what you would have done if you had some.
Well, I could. It's so the planes are x, y, z equals 0, so it'd be 1, 1, 1. And then the next normal would be 1, 2, and 4.
Okay. Now you want the angle between those two. It's, oh, they only want the cosine. Okay, so the cosine of the angle is the dot product divided by their magnitudes. Right, 1 and 1 gets me 1, 1 and 2 gets me 2, 4 and 1 gets me 4. Square root of 3. Oh, 16, 21. Top guy is what, 7. Square root of what, 63. 63 is 9 times 7. So that's 3 root 7. Rationalize the denominator. You get 7 root 7 over 3 times 7. Oh, the 7s cancel. Oh, it ends up being quite nice. Root 7 over 3.
So that's actually the answer I got. But when
It's-
I write it in, the
Oh, you don't. Well, you might have, because if you did, you got exactly what I did. That's 9. That's 9. 4, 2, and 1. No, it's not.
Wait. Yeah.
Yeah, I was right the first time. My God. I don't even trust myself now. Okay, you got that? And it didn't like it?
well, so I wrote cosine -1. Actually, sorry, inverse cosine to 7 over 3 square root of 7. I mean, I didn't rationalize it yet, but
Right. But that is eventually going to become that, right?
yeah,
James, I think if it asks for the cosine of it, you just plug in the number, not the cosine inverse.
So you only need to put this piece in.
I'm pretty sure,
You
yeah.
don't need to type in that piece. They probably have this piece here, and you just have a box for the number.
I
Is
think
that
it
how
just
they-
asks for the cosine.
Right, so you just put in this piece and not the inverse cosine part. That makes sense.
yeah, that makes sense.
So that might be okay. They might not worry about that not being simplified. They're kind of hit and miss on how simplified things have to be. Is that true? Some WebAssigns, it's okay, and then the next time you have to make it prettier because they didn't like it. You got a chance to do it, to check it out?
Trying
Just-
it out.
Okay.
And it liked it.
This version here or this one?
Well, I did the rationalized one.
This one. Okay.
Yeah.
Well, next time if you've got time, just out of curiosity, try the uglier one. See if it takes it. Has anybody done questions where the ugly one was fine, or did you have to make it pretty?
For me, it's accepted both.
Right. So it's at least in the questions you've done, it's been generous. Okay. Any other questions? So that was just a simple what WebAssign wanted you to write down, because you had the answer, right? You just didn't realize they didn't want you to write down this bit.
Yeah, that's what I figured.
Have we anything else?
I have one more question about,
Yeah.
So today when we were going over the problem where the curves intersect and we had to find their angle of intersection,
Yes.
yeah, if you could just pull out that sheet real quick so I could point exactly to the part.
I'll
of the
try.
problem I'm referring to.
There's a lot of sheets here. Let's see. Let's definitely know that one. That's a start, so it won't be that. Won't be that. This is integral, so it's not that. Looks like this one.
Perfect. Yeah. So, so at the top we have like R1 of T, R2 of S, and then right
Yeah.
below it we have the 1, 2, and 3. And
Mm-hmm.
yeah, you found T equals 1 and S equals 2. How did you, like, I don't really understand how you
Well,
got
oh, I did that by cheating, by making them that, so I wouldn't need to solve it. But how you would do it if you didn't have the ability to just pick up telepathy is that you would take, for instance, question information here, right? And you put it into equation 2. Now, since t is s minus 1, right, which is, you can see that, then this becomes s minus 1 squared is 2s take away 3. So what you're trying to do is you're trying to reduce it from 2 variables to an equation that only has 1 variable, because we know how to solve one variable equations. Now, this has still got a fair amount of work, but it's FOIL it out. Bring this across. Factor it. S is equal to 2. Now I know S. T is S take away 1.
Oh, okay, that makes a lot of sense.
Right. Now, you have 3 equations to play with. It might not be 1 and 2 are any good, right? Remember the first one that just freaked me out and I couldn't figure out what the heck it was because it wasn't working. If I just done 1 and 3 or 2 and 3, I wouldn't have had a problem, right? It would have solved. So if you try equation 1 and 2 and it just disappears on you and think, well, I can't get anything, try 1 and 3. Hopefully that'll work. And if all else fails, 2 and 3 will work. One of them has to work, right? One of them has to be solvable. And once you know one of the variables, you're guaranteed to get the other one for free.
All right. Well, that makes sense. So thank you very much.
Okay, you're welcome. Have we any more questions, guys?
I gained 2 during this. So the first one is, I believe it was the first problem that you covered during this lecture. Where was it? And it's the, how to find the equation of rotation.
All my papers are all jumbled up, but that doesn't matter. I can find it wherever it is.
So let's see, it looks like it was problem number 11.
I've still got the questions handy. So let me have a look at, oh no, it's integration. Oh, I got it. Find the parametric equation for the tangent line, that one?
Yes, and my, yeah.
Keep talking, I'm listening.
So we had, my question isn't necessarily how to solve the work, it was about the notation you used. So at the very beginning, we're given a vector equation, R of t.
Yeah.
And at the very end, we found another equation.
Yeah, technically, if I'm going to call that R, I guess to distinguish them, maybe I should give them numbers because they're not the same thing.
Okay, just wanted to make sure they were different.
Yeah. It just, you know, like f of x is like a catch-all for everything. And sometimes another thing is also called f of x, even although it's not the same thing as the first f of x. It's just a careless notation by me.